Okay, so in this lecture, we are going to talk about or introduce a few more important distribution, which is the chi-square distribution, the t distribution, and the f distribution. And then we are going to use the idea of method of transformation to introduce these new distributions, as they can be derived from the quadratic form of standard normal distribution. So we are going to be extending the idea from last week and then using it to introduce a few more distribution. And first of all, I would like to use, or just for the beginning of the lecture, I would like to, using another example just to refresh your memory on the method of transformation. So here, suppose we have a random variable x that follow a gamma distribution with parameter alpha 1 and then beta. And then we also have another random variable y that also follow a gamma distribution, but with parameter alpha 2, and they share the same beta. And then we also know that the x and the y are independent. Okay, so now we can start to talk about our construction. So let's suppose we have a new random variable u, and then we're define u as the x plus y. And then we also have a new random variable v, and then we're going to define it as x over x plus y. So our goal through the method of transformation is that we need to find the joint distribution for our new random variable u and v. So what we have is first of all, is the marginal distribution for x and the marginal for y. Because they are independent, so we know the joint is just the joint of x and y is the product of the marginal of x multiplied by the marginal of y. But our goal is to find the joint distribution for u and v. So we are going to use the method of transformation to approach this problem. And also, if you want to use the notation from last time, you can refer these by construction as your function g. And then another important component in the method of transformation is that you need to find the inverse function, which is the input for u and v, and then to get the x and y, and then to make the change in the density function. So here, let's find the function h1 inverse in terms of u and v. So here, let's see. We can first rewrite the random variable v as x over u, which is the x plus y, so that we know that the x can be expressed as u multiplied by v. And this is your first h1 inverse. And then for the y, we can get in the following way. So u is equal to x plus y, and then we know that the x can be written as u multiplied by v. So we only have one y, and then we can rewrite y equal to u multiplied by 1 minus v. Okay, so this is your h1 inverse in terms of u and v. As you input u and v, you should get x. Here is your h2. You input u and v, you should get your y. Okay, so now you have your function g and your function h inverse. We can talk about the Jacobian matrix. So again, we introduce J1 and J2, and then you can use either of them to find your joint distribution for f of u and v. So the choice or which one to choose, it really depends on which of the derivative is easier to find. So in this examples, I'm going to use J1. So you can refer J1, the formula from your notes from last time, which is the Jacobian matrix that is constructed in the following way. So the first entry is dx du, and then you have dx dv, and you have dy du, and then dy dv. Okay. And now let's calculate each of the terms here. So determinant of a 2x2 entries. So here dx du, which is just a v here, and then dx dv should just be a u, and then dy du, which should just be 1 minus v, and then dy dv should just be one copy of u. And don't forget there's a negative sign, so negative u, and then the determinant of that. So the product of the diagonal minus the product of the off diagonal. So you will have negative uv and then minus u multiplied by 1 minus v. And then let's further simplify this. Minus u plus uv. So you should only have one copy of negative u. Okay, so that's the determinant of this Jacobian matrix. Yeah, and then you can also use J2. And then don't forget, if you use J2, when you take the absolute value, you should take the inverse. And then the details is just referring from the formula from last time that I provided. Okay, so now we have the Jacobian. We can make the change of variables from the density function. So first of all, let's rewrite f of x and y. So they have the gamma distribution. So they should have the following expression. So x raised to the power of alpha 1 minus 1, and then exponential of negative x over beta, and then a gamma function for alpha 1, and then a beta raised to the power of alpha 1. And also, because they are independent, so you can write it as the marginal of x multiplied by the marginal of y. So y of a2 minus alpha 2 minus 1 e of x e of y over beta, and then gamma of alpha 2, and then beta of alpha 2. Okay, so that is the joint distribution for x and y. But in our objective, our objective is to find the density or the joint density for u and v. So here we are going to make the change for the x and y. So we rewrite x as u and v. So we have the following: uv alpha 1 minus 1. And then let me write using the exp notation, and then you will have uv over beta. Okay, and then the normalizing constant does not involving x and y, so it stays the same. Okay, and then for y, let's see, we rewrite y as u minus uv. So let's also write it down. We will have u minus uv. So alpha 2 minus 1 exp for negative u minus uv over beta. Okay, and then the normalizing constant stay the same. We will have gamma of alpha 2, beta alpha 2. And don't forget, whenever you make the change of variables, there's a third term here, which is the Jacobian. So here we choose J1, so we just use the absolute value of J1. And then, yes, so if you use J2, don't forget to multiply by the absolute value of J2 inverse. Don't forget about the third term here. Okay, and then for our case, because we know J1, it's negative u from here, so that the absolute value is just one copy of u. Okay, so now we can further simplify this expression. So we are going to group the things correspondingly. So for example, we have u here. So let's separate the u. We have a power of alpha 1, and okay, so this is u multiplied by 1 minus u, so that the u here will also have a power of alpha 2 minus 1. So let's plus a alpha 2 and then minus the 2 from minus 1 and minus 1. And don't forget we have one more copy, so plus another 1. Okay, so that should aggregate all the u's here. Now let's talk about v. So from here we have a alpha 1 minus a 1. Here we have 1 minus v, so 1 minus v alpha 2 minus a 1. And yes, I think that should conclude all the v terms. And then we're going to group the exponential here. So exponential, here we have a uv over beta. We also have a plus uv of beta. So when you group them together, you only have one copy of minus u over beta. Okay, and then we have the following normalizing constant. Alpha 1 plus alpha 2. Okay, so this is the joint distribution for u and v. But if you're looking at this expression, you might not recognize anything from it. But now let's multiply in the end by a value of 1. And then we are going to rewrite the 1 in the following way. Alpha 1 plus alpha 2 divided by alpha 1 plus alpha 2. So this is just equal to 1. So it does not change anything regarding this density function here. But we are going to rewrite this density function in another way. So here we are going to write u of alpha 1 plus alpha 2 minus a 1. And then you have the exponential negative u over beta from here. And then I'm going to using this part. So gamma function of alpha 1 plus alpha 2. And then beta of alpha 1 plus alpha 2 from here. Okay, so that's everything involving u. And then multiply. Okay, so let me not use, okay, just in case, use a dot then. Okay, then let's take a look at the v. So we are going to write the well, right now I'm still not going to make the conclusion, so I'm just going to write down the things. So we have v of alpha 1 minus 1, 1 minus v alpha 2 minus 1. And then here I'm going to write function beta function, and then which input alpha 1 comma alpha 2. Okay, so this beta function, let me write it a little bit, okay, here. So I'm going to introduce this beta function here, which is the gamma of alpha 1 multiplied by gamma of alpha 2 divided by gamma function of alpha 1 plus alpha 2. So here I'm using the numerator and then the 2 gamma function from here, but this is a division, so you take the inverse, so this becomes the denominator and this becomes the numerator because you are dividing in the denominator. Okay, so this is what we define as a beta function. And then after we rewrite this joint distribution in this way, we see that this x, this u here, it's actually following a gamma distribution with the parameter alpha 1 plus alpha 2, and then the beta is still the same. And then for this one, this is a new distribution called the beta distribution. And then it takes 2 parameters, alpha 1 and the alpha 2. So here, this beta is referring that this is a beta distribution, and this b here is referring to a beta function, that when you input alpha 1, alpha 2, you have this evaluated, and then that will be your result for your output. And then this is referring to the beta distribution, which is also showing up in your homework. Okay, so the idea here is that we start from the distribution of a gamma for x and y. We have 2 particular functions of transformation denoted as g. And then we derive the inverse function, the Jacobian, making the change, and then we obtain the joint distribution for u and v. And then in the end, we find out that this is actually a product of a gamma distribution and a beta distribution. And also, because they can be separated into 2 marginal distributions, we also know that the u and the v are also independent. Okay, so we start by x and y, 2 gamma, they are independent. Make the change. So the new distribution, u and that has a product of a gamma and a beta. And then we also know that u and v are independent. Okay, so this is just to refresh your memory on the method of transformation. So next, we are going to talk about some other new distributions. So first of all, I would like to introduce the distribution of a chi-square. And then I'm going to introduce this distribution by its own construction. So here is the chi-square distribution. Okay, so let me first use z and then maybe zi following a standard normal distribution. And then for z1, let's say to zk, they identically, and then they're also independent following the standard normal 0, 1. And then I'm going to say that this v that we constructed in the following way. So zi square. And then I'm going to, and then the one, so zi square. So when you construct it in this way, first of all, they need to be independent, and they all come from standard normal. When you take the square, sum them over of a k copies, and this will following a chi-square distribution with degree of freedom k. Okay, so for this one, we are going to verify this by using the method of by using a moment generating function. So let's derive the moment generating function for this new random variable v. And because this is a sum and then they are independent, so this is equal to the product from 1 to k, the moment generating function for zi squared. Again, it's a function of t. Okay, so let me okay, so here maybe we use the definition for the moment generating function. So again, product from 1 to k, and then the expected value for et zi squared. Okay, that's that. And maybe let me start another line here. Okay, so we should have the product from 1 to k, and then the integral from negative infinity to positive infinity, and then e of t zi squared. And then zi is the standard normal, so we will have the following density function when we're calculating this expectation. So 1/2 zi squared, and then dzi. Okay, so that is the expected value or the moment generating function for zi squared. Okay, so now let's simplify this formula. Okay, so here we still have the product from 1 to k, and then I'm going to take the integral. So I'm going to leave some space in here for now, and then we will have 1 over 2 pi. And then I'm going to group the two exponential terms here, and then I'm going to write it in the following way. So I'm going to write it as the negative sign zi squared on the numerator, and then you will have 2 of 1 minus 2t, and then also a inverse here. So I'm just grouping, maybe I can elaborate a little bit here. This is e of, or maybe exp negative 1/2. Let me use zi squared minus. Okay, so maybe let me so 1 minus a 2t. Okay, so I'm going to put this in the denominator, and then by adding an inverse, and then this 2 is just to cancel out that because there's no 2 here. So I'm just, after grouping these two, I write it in the denominator. So this is the grouping by grouping this exponential with this exponential. Okay, so next I'm also going to introduce a 1 as a product, or to multiplying this thing by not changing this quantity here. And I'm going to construct the 1 in the following way. So 1 minus 2t raised to the power of 1/2, and then also divided by 1 minus 2t, 1/2. Okay, so now we have the following expression. So I'm going to bring one copy, or this numerator outside. And then for the rest inside the integral, we have 2 2 pi, and then 1 minus a 2t, and don't forget there's a inverse first, and then taking the square root. Okay, that's that. So zi square over 2, 1 minus 2t inverse, and then dzi. Okay, so now let's take a look at this form. This is essentially a density function for a normal random variables, and we have this as our constructed density function. So again, this is zi minus the 0 square. So we have 0 as the mean, but the variance. So what we started is the standard normal, but after this construction, now this density function is for the zi that following the 1 minus a 2t inverse. So this as your new sigma square. Okay. And also it gives you the condition that t need to less than 1/2. Okay. So you also need to make sure that you have this condition to consider. Okay. But the point here is that the integral here is a normal distribution, not standard anymore, because this is not 1, but you have, it's still going to be a density function. So your result should be I from 1 to k, and then 1 minus 2t negative 1/2, as this integrates from negative infinity to positive infinity equal to 1. So you will have this, and then because they are all identical or identically distributed, or here it does not involving any subscript I, so that you will have the following k over 2. So this is the, again, to remind you, the moment generator function for v, the one that we derive. And this is the moment generator function for chi-square. So we know that the v following a chi-square distribution, degree of freedom k. And then another thing to point out here is that this formulation, you should already be very familiar, as this is the gamma distribution. So we will have v is also a gamma distribution. And then the alpha here, it's k over 2. This is the negative alpha. And here is the 1 minus beta t. So the beta is equal to 2. So we know that the v is a chi-square distribution, degree of freedom k. But this chi-square distribution is essentially a special case of a gamma distribution with this alpha and then this beta. So you can also, so the chi-square random variable also has a similar form for the density function as the gamma distribution. So you can always use gamma density function to express your chi-square distribution, their density function. Okay, so here we just want to point out that the chi-square random variable can be constructed from the standard normal distribution by taking the square and then some k copies of them to get the chi-square distribution, degree of freedom k. So this is the construction. So if you want, you can also think about this is your function g that input a z, and then you will get a new transformation for a, let's say, the univariate case. Okay. And then now we have introduced the chi-square distribution. Here I want to talk about the t distribution. Okay, so t distribution. Okay, so t distribution can also be constructed by all the from the information that we know from before. So I'm going to write in the following way. So let's write z. Okay, so let me first define z then. It's a standard normal. And then let's define v following a chi-square, degree of freedom k. Okay, so now I'm going to make the following. So if you draw samples from standard normal and then from a chi-square, then the following transformation should follow a t distribution, degree of freedom k. Okay, so and also the z and the v, the chi-square, should be independent. Okay, so if you draw sample from a normal and also a chi-square, if you take this transformation, this resulting new random variable follow a t distribution, degree of freedom k. Okay, so now we are going to derive the density function for a t distribution, and by using the method of transformation. Okay, so maybe let me write it in. Okay, so let's first make our transformation. Let's define let's make first okay, so what we have is the z and the v here, which is because they are independent, f of z multiplied by f of v. But what we want is the f of t. Okay, so let me define this as capital T. Okay. And also notice that this is bivariate distribution. This is a marginal distribution. So our strategy here is that we first use this, and then through some transformation to get f of t and s. And then we take the integral. So let me put it here. Take the integral with respect to s. And then this will give you the f of t, the marginal. Oh. Okay, so that will be our strategy. And then we also know this is standard normal, this is chi-square or gamma. So we can make all those transformations. Okay. So first, let's define. Okay, so maybe starting from new. Okay, let me erase this part. Let's define t in this way. And then let's define s as v. Okay, so we have two more random variables. So again, the idea is from the density function from z and the v to get t and the s, and then taking another integral to get t, the margin of t. That will be our strategy. So now let's first define these two random variables. So this is your, let's say, your g1 and then g2. So here you can also consider this is like a plus 0 multiplied by z, so that this is a function of z and v. This is also a function of z and v. Okay, so by our procedure, we need to derive the h inverse. So for h1, which is the z here, we are going to write t multiply by v divided by k, and v is also s, so s divided by k square root. So this is your h inverse, only inputting t and the s. So g1 take z and v to give you t or s, and then h inverse takes in t and s will give you z. And then for v, this is also s, and then if you want plus 0 and t, you can always construct in the following way. So h2 inverse for t and the s. Okay, so once we have the g and the h inverse, let's make the Jacobian for the transformation. So here we are going to use j2. Determinant of the following. So dt, the one that we make the change to the z, the original. So dv, ds, dz, ds, dv. And then which one to choose, j1 or j2, depend on how easy or difficult these derivatives are. So in our case, maybe it's simpler. Okay, so dt over z should be 1 over v divided by k square root. Okay, and then dt, dv for now can be a little bit difficult. Let me just write down the form. Because the v is in the denominator and also have a square root, so we have a negative 1/2 for the denominator and the square root, multiply by square root of k. This is a constant, and then because it's divided, but so it will be on the numerator. And then you will have your z also from the numerator, and then it's nothing to do with the v, and then you will have v raised to the power of 3 over 2. So negative 1/2 minus a 1. Okay. Although this part can be difficult, but ds, dz is 0. So when you take the product, this will cancel out. So if you don't want to calculate, this is gone already. ds, dv, just like 1. Okay, so this is our Jacobian. Then the determinant, and then let me write it here. So j2 is equal to this divided by that, so k over v. Here, if you want, you can also change it here, because when you make the transformation, your function need to be in terms of t and s only. So here you can also write the v as s, and then the square root. I think that is j2. Yes. Okay, after that, we need to getting the distribution. So let me okay, so square root of k over s. Okay, then I can remove this part. Okay, so now starting our t and the s function. So we can get that from, I already erased that, so f of z and v is equal to f of z multiplied by f of v, because they are independent. Okay, so first of all, let's start from the density function for standard normal. So square root of 2 pi exponential negative 1/2, and then we will have z squared. Z squared is this one, so we should have s over k, z squared, so a t squared. Okay, then for the chi-square distribution, again, as we mentioned, that is a gamma distribution, so we can use gamma to express that. So v following gamma, so we write v in terms of s. So you will have s raised to the power of alpha. And okay, so let me write the v with degree of freedom k should follow a gamma distribution k over 2 and 2, right? Here. Okay, so we're going to use gamma formulation to write the chi-square distribution. So we're going to use v after we change it to s raised to the power of k over 2. This is your alpha minus a 1. Okay, and then you will have exponential of negative s over beta. So beta is a 2. Okay, and then you will have your gamma function for alpha, so k over 2. And then beta raised to the power of alpha. So beta is a 2, alpha is k over 2. Okay, so this is your density function for gamma, but essentially it's a chi-square. And then don't forget the Jacobian. So we need to take the inverse because we're using J2. So S over K here. Okay, so J2 absolute value inverse. Okay, so this is our joint density function for T and the S. Okay, so first let's simplify this. So this is equal to 2 pi k. So this 2 pi and this k, okay, multiply by gamma function k over 2 from here. Okay, and then 2 raised to the power of k over 2. So everything on the denominator is here. And then let's write down the rest of the terms. So we have one copy here, s raised to the power of 1/2. So here we have k plus 1 over 2 minus a 1. and then exponential, and then combining these two terms. So you should have -1/2 from here and here, and they all share a copy of s, so we can write the s outside. And then we have t squared over k from here, minus a 1, because here is a sum of 1, but you need to take care of the minus sign here. Wait a second. So oh, okay, so you need to plus a 1, because this is a minus a 1, so you will have to plus the 1 here. Okay, and then yes, you have all the terms. Okay, so now let's okay, so just to remind you, this is the joint for t and the s. So as you can see, they're only involving s and the t. And now what we really want is the marginal for t. So you need to integrate with respect to s to get the marginal of t. And then this will be the density function for your t distribution. Okay, so let's see. You have the same normalizing constant here. Okay, and now integrate over s, k plus 1 over 2 minus a 1 exponential of negative s over, let me write it in this way. So t squared over k plus 1 inverse, grouping that, ds. Okay, so now if you're looking at this formulation, you will recognize that this is a kernel function for a gamma distribution. Okay, so that alpha equal to k plus 1 over 2, and then beta it's 2 times t squared over k plus 1, and then inverse here. Okay, so now we know the result that you integrate a kernel function, you should get a formulation in the following way. So again, this constant stay the same. 2 pi k over 2, 2 of k over 2, and then you should have a gamma function of alpha, so gamma of k plus 1 over 2, and then beta raised to the power of alpha, so you have a 2 of k plus 1 over 2, and then t squared over k plus 1 inverse, and then raised to the power of alpha, so negative k plus 1 over 2. Okay, so let's further simplify by canceling some of the terms. So you have let's see, so you have a k from here am I? Let me. Okay, so wait a second. So you should have a gamma function of k plus 1 over 2 for this one. I see. Okay, so this one, place it here, and then you will have a square root of pi k. So this 2, you have 1/2, 2 raised to the power of 1/2, and you have 2 raised to the power of k plus 2, k over 2. So together you have 2 of k plus 1 over 2, and then it cancels out of this, so you only left with pi k. Okay, and then so this one is good, this one is good, this one is good, and then you have the gamma function of k over 2. Okay, so this is also taken care, and then you just have t squared over k plus 1 negative k plus 1 over 2. Okay, so now this expression is the probability density function for t distribution degree of freedom k. Okay, so just to summarize the construction of z. Okay, so let me just to summarize for this lecture is that when you have just a summary, so when you have z follow standard normal 1, summation of I from 1 to k zi square following a chi-square distribution degree of freedom k. And then when you have z that also following normal, and then a v divided by k, where v following a chi-square distribution degree of freedom k, when you do that, this will give you a t distribution degree of freedom k. Okay, so as you can see that we introduced the normal distribution, and then we use momentary function to show that this following chi-square, and then we use the method of transformation to get the density function for the t distribution, and then they are all centered around the normal distribution. And yes, so many of this distribution is originated or can be constructed or derived from the standard normal distribution. And then in the next lecture, we will going to talk about the F distribution. And all these distributions are very useful for hypothesis testing. And then I think you have already been using these for a long time. But in this lecture, we are just going to use all these mathematical tools such as momentary function and transformation to provide or derive all these statistical distributions or concepts here.